survive the first day. My name is Marina Marjanovic, and I'm one of the organizers of this Biophotonics Summer School for the 5th year. So if you have any questions, any comments, please let us know. And I'm chairing this afternoon session. So it's my great pleasure to introduce the first speaker, Dr. Beniamino Barbieri, who is actually owner of a local company that's making a biomedical instrumentation. And he's going to give a talk today and tomorrow morning about the principles of fluorescence. Because a lot of these instruments, as I understand, are based on the fluorescence techniques and methods.
Thank you. Maybe we can have the light reduced a little bit, please. Thank you. So yes, good afternoon. The idea is just to introduce you to a few concepts of fluorescence. In the past few years, this technique has become more ubiquitous because of the increased number of applications. And so it is important, you will find it in several tests, in instruments, and it's important at least to grasp the basic concept of fluorescence. First off, what is fluorescence? Fluorescence is emission of light upon the absorption of atom molecules of photons. And the question is how we can use this phenomenon to understand better what's happening with our samples. The main reason the fluorescence became so popular in the past 10, 15 years is due to two issues, two things. One is the invention of the lasers, so light sources that makes the application of fluorescence easy to perform. You can go to open a Thorlabs catalog, buy a laser, and build an instrument. The other one, which is more important, is the development of these fluorescent probes that we can use as sensors for specific applications. Not only that, but also with the introduction of the family of green fluorescence proteins, now we can grow some proteins that are fluorescent and then follow how some of the processes within the cell occurs. These are common fluorophores and commonly used fluorophores like fluorescein, rhodamine, kinin, but there are so many. There are full catalogs, there are hundreds and hundreds of fluorophores. So typically you select a fluorophore depending upon the specific problem that you are trying to solve and to address. Why fluorescence? First, because it's nice, it's beautiful, it's colorful, and but second, because it provides you with some information about the environment where these molecules are staying. In fact, if I have a fluorescence probe, the characteristics, the properties of the fluorescence probes are affected by pH, by electrical fields, are affected by the presence of other fluorophores. So we can use these facts in order to understand better what's happening to a specific problem that we're trying to tackle. And of course, in the past 10 years, with the use of confocal microscopes. Question?
How does viscosity affect the fluorescence of materials?
Because it changes the index of refraction, and then the lifetime of the fluorescence is changed. In fact, there are some applications where people measure the index of refraction within a cell. So a cell is a complex structure. There are proteins that are produced, proteins that go in and out of the cell, and each protein has its own task. So now, for the first time, it's possible to make what is called quantitative biology, where people are trying to look inside the cell, but they are trying to look at the using phenomenon and the molecular interactions that occur inside the cell. So back to your question, yes, people also measure some of these parameters at this specific locations inside the cell. So this is all possible because of all this development of fluorescence. And what is relevant is that with a little extra trouble, it's actually possible to detect one molecule only. This is a big achievement that has it has only been reached after 1996, 1997, so it's just in recent years. And while at the beginning there were only a few laboratories in the world that were claiming to detect single molecules, now practically almost everybody, every laboratory that is working in fluorescence and has a microscope can actually have the capability to measure single molecule detection. Well, these are some of the general applications of molecular dynamics and studies. Of course, we can grow, as I said, GFP proteins and make these animals colored, but there are also arrays which are used in drug discovery in the pharmaceutical industries. And these are some of the instruments that are used in the fluorescence of spectrophotometers, and you will see next week, you will have some practicals on spectrophotometers, on confocal microscopes, flow cytometry, sequencing, microwave plate readers, immunoassay. So there are a lot of applications about fluorescence, both in research but also in industry. Now, a couple of words about the discovery of the phenomenon. The phenomenon was first reported in around 1560, 1565, when the Spaniards at the time were trying to understand and report some of the discoveries in the New World. And Nicolas Monarders, these physicians, reported that the Indians were using a particularly piece of wood from a tree, and this tree would leave when left in water, would make the water colorful with a bluish color. And they were using this tree to cure some ailments. And so this raised the curiosity of these people who brought it back to Europe. And Charles Delecluse gave the name of Lignum nephriticum, or kidney wood, because apparently it was helping some diseases that were related to the kidney. And in fact, there was a gentleman, John Frampton, had been living in Spain for several years. When he returned to England, translated from the Latin and the Spanish some of the Monard's work, and wrote this colorful piece of report about the kidney wood. After about 100 years, Robert Boyle of the Boyle law of pressure and volume in gases was intrigued by the phenomenon and tried to have a better understanding of what's happening. And he discovered that two things, that if the solution was washed several times, the piece of wood lost little by little its property. So there was less of this color or this essence or this substance going into solution. But he also discovered that by changing the pH, so making the solution more acidic or less acidic, the fluorescence would increase or decrease. So in a sense, he was discovering the first pH meter. After about 100 years, Herschel was studying the properties of another interesting substance that was used by Indians and also by Africans to cure some ailments, and that was the kyanine sulfate. And he discovered the fluorescence from kyanine sulfate and called the phenomenon epipolyc dispersion. So this is interesting because if we would have followed his suggestion today, we wouldn't be here talking about fluorescence, but we will here to talk about the property of epipolyc dispersion. Fortunately, there was another fellow by the name of Stokes who, about in 1852, published this massive paper. Practically, it was like a book, 100 pages. Today, we can make 10 of these papers out of this. And he was trying to understand the phenomenon of kyanine sulfate and the fluorescence. And he actually made in this paper a lot of interesting observation. But one of the interesting suggestions was that he suggested the name fluorescence, and from that moment on, it stuck to the phenomenon. We want to look a little bit at his experiments. At the time, there were no laser. The light sources were very limited, so people were experiment using the light from the sun. So typically, they would just stay in a dark room, well, wait until there was the sun, because if it was cloudy, they couldn't do the experiment, and close the windows, make a hole in the windows so that a little ray beam of light would enter through the windows. So he would pass the light through a prism, and the phenomenon had been discovered by Newton several years before. And when the light, the white light, goes through the prism, it is being separated in colors, in wavelengths, so like the rainbow that we know today. And what he discovered was that when he had this solution with Kynan sulfate, and he was placing it in this far end of the spectrum, nothing would happen. But as he moved the solution towards the violet, ultraviolet, suddenly the solution became color. And became color, giving a bluish type of color. And in fact, this was his observation in the paper. So he understood that the fluorescence typically occurs at wavelengths which are longer than the excitation. And this phenomenon, we call it the Stokes shift today. And by the way, in 1864, he also proposed to use fluorescence to make some analytical instrumentation. And then when we go to the end of the century, when the quantum mechanics is being proposed, and a lot of the properties of the fluorescence are being explained, and they are clarified, and we use these properties all the way today. Now, let's talk a little bit about business. When we talk about fluorescence, there are 5 properties that characterize a substance. The excitation and emission spectrum. So this is the range of wavelengths that are absorbed by the substance, the range of wavelengths which are emitted by the substance once they are excited, the quantum yield, the lifetime, and then the polarization. So briefly, I will touch on each of these properties to show to you how they are being used. Now, first off, what is fluorescence from a quantum mechanical standpoint? This is a classical Perrin-Jablonski diagram, and if you remember from your physical chemistry courses, molecules have a ground state, a first excited state, and they might have other states. Close to the excited states and the ground states, there are vibrational levels and rotational levels. So what happens is that we radiate a molecule with photons, and the electrons finish up into the excited states. And you see here that you can use wavelengths, photons of different wavelengths, to go into the excited states. If the wavelength is not long enough, there is no transition. The electron doesn't go to the excited states. But there is a range of wavelengths where the molecule can absorb. Once the molecule is in the excited states, it rapidly decays to the first excited states, and from here it emits photons. And all the photons are emitted from the first excited states. And again, there is a range of emission wavelengths because of the vibrational and rotational levels associated with the ground state. Now, technically, the situation is also a little more complicated because sometimes not all the photons are emitted. So there are what is called radiative decays, but there are also intercrossing systems with what is called in quantum mechanics triplet states that give rise to phosphorescence. And there are non-radiative decays. It might happen that a molecule in the excited states collides with another molecule, and so the energy is lost. So we don't have a photon anymore. although the energy, of course, is conserved. So this is a depiction of a excitation spectrum acquired with an instrument. So this is the range of excitation wavelengths that is absorbed by this specific substance, rose Bengal. And this is the emission spectrum. So what it means is that if we excite at any wavelengths in the excitation spectrum, so let's say roughly all the way, well, 600 is the limit, but let's say around 570, 580, we can get an emission spectrum that looks like this one. Now, if we superimpose both, we see some of the properties of the excitation emission spectrum. The emission always occurs to longer wavelengths, as proposed by Stokes. And the emission spectrum and the excitation spectrums have some similarities. In fact, they look like the mirror image of one of the other. And this is because of the way the quantum levels in the molecules are depicted. It's not a general rule, but is a rule that is followed by most of the substances. And this is as far as we go for excitation emission spectrum. The second parameters that, or third parameter that we want to consider is the quantum yield. So once the molecule absorbs the photons, it re-emits the photons. So the quantum yield is, can be understood as the number of photons that are emitted over the total number of photons that are absorbed by the molecule. So if we keep in mind the rate of decay of the per range Jablonski, we can write the quantum yield in this way. Why is the quantum yield interesting? This is a table that I got from a book. Sorry? KR is the radiative, so the photons. NR, non-radiative. So the fact that a molecule might collide with another molecules, and so the energy is transferred to the other molecule, but not in form of photons, of light. This is a table that reports the quantum yield of a few substances, benzene, tryptophan, and you can see that we go the way from low values, like 0.05, to 1, like rhodamine. Well, now, if I want to build an experiment and I want to use a fluorophore because I want to follow a specific parameter, I select a fluorophore with a quantum yield that is high because I want to see the signal. And so that's why it's always important when selecting a fluorophore to look at this parameter and just say, well, if the quantum yield is so low, forget about it. Similarly, there are some substances that, for instance, the nucleic acids, DNA, RNA, they have, people think they don't have any fluorescence, which is true. If you put them into a fluorometer, you don't see any signal, but it is not true. They do have a signal, but the quantum yield is just in the thousands. So still those substances have a quantum yield. Anyway, the lesson here again is if I want to build an experiment, let me select a probe that has a high quantum yield, like a 1, 0.9, and or 0.6, but forget about the ones that have a low quantum yield. Now, another important parameter is the decay time. And this is very important because it's used in several applications. And sometimes it's also a little more difficult to understand, so we need to pay a little more attention. So think again of the excited states of the molecule. And we have a population of molecules, we send some light, some molecules finish up in the excited states, and now we want to see how they decay. So the rate of changing of the population of the first excited states, N1, is equal to minus the decay, radiative and non-radiative, the same terminology, and is proportional to the number of molecules that we have there, plus Another function that it depends if we send photons in a pulse way or in a continuous way. Well, let's forget about this function. This is an equation that is easy to solve, and so it gives, this is the solution. So the solution is an exponential decay, where tau is equal to the inverse of the sum of the decay rate, radiative and non-radiative. This is the decay time of the molecule. In other words, we can depict this one on a graph. It has an exponential decay. When after a time tau, we get the number of molecules in the excited states is the original number of molecules divided by E, which is about 37%. This is the meaning of decay time. It's very important to understand because people think, what is the decay time of one molecule? In reality, the decay time is a parameter that involves a collection of molecules. We cannot assign it to a specific molecule. Within the collection, some molecules decay with a decay time that is short, some long, but what we call the decay time is actually this parameter tau. Now, if we go back to the definition of the quantum yield, we can then define the quantum yield in terms of decay times. This is the radiative, and this is the natural decay time. Anyway, the lifetime can also be calculated, and in fact, back in the 60s, Strickler and came up with this equation to calculate the lifetime of a single exponential decay. Kind of a complicated formula. It contains the speed of light, the index of refraction, the Avogadro number, the distribution of the emission spectrum, absorption spectrum, the extinction coefficient. So it's so complicated that usually, even if you try to solve it, it never gives the results that you are actually measuring with the molecule. Now, the lifetime cannot be predicted also by looking at the structure of the molecules. These are examples of polycyclic aromatic hydrocarbons. Naphthalene, 2 rings, 2.7 nanoseconds. If we had another rings, we go to 5.1. Well, if you have more rings, it drops to 4.3. This structure goes all the way to 400 nanoseconds. So there is no way, a priori, to have an idea, I guess, of what the value of the lifetime is. The only solution is to measure the lifetime. So use an instrument that is built to measure the decay time. And you will see next week an example of one of these instruments during the practical. Now, the lifetime also changes a lot depending upon the environment. This is ANS. In water, it's about 100 picoseconds, but it can become 10 nanoseconds if ANS is bound to a protein. Titanium bromide, well, from 1.8, it goes to 22 nanoseconds, and 27 when it's bound to tRNA. Tryptophan, which is one of the amino acids in the proteins, it varies from 100 picoseconds all the way to about 10 nanoseconds, depending upon the location in the protein. Is it outside? Is it inside? Is it close to other tryptophan? Is it alone? So again, the lesson is no way to predict what the lifetime is, no way from the structure or from the theory. The lesson is measure it. Take one of these instruments and do the measurements. Here I will make a little digression on the instrumentation. There are 2 ways to measure the decay time. One is called time domain, the other one is frequency domain. In time domain, the idea is just to hit your fluorophore with a narrow pulse of light, and then to detect the photons that decay after a certain time, and build an histogram, and then the fitting of the histogram will give you the decay time, which is the tau here. In frequency domain, typically you use CW sources, although you can also use in frequency domain pulse sources, but I will not go into those details. The idea in frequency domain is that you modulate the light source, and you go to detect the phase shift of the fluorescence and the demodulation. So the emission is delayed to the excitation. It is delayed because the molecule spends some time in the excited states and is demodulated. So the ratio peak to valley is less than the peak to valley of the excitation. And there are these relationships that relate the phase angle to the decay time or the demodulation to the decay time. Sorry?
Which factor is considering the environment because lifetime may vary from solvents to solvents?
Yes. So let's say if you have your sample, let's say if you have a yeah.
Same one if you have like green or something like that, you will discuss the lifetime will change.
Correct. Correct.
Which factor in that equation consider that part?
Oh no, these are just general, you mean these equations? No, these are just general equations that are used in the instruments to measure the lifetime. So let's say that then I measure tryptophan and I change the temperature. So I set the instruments at 10 degrees and I measure a lifetime. 15 degrees, I measure another lifetime. So that is an experimental finding that is related to the tryptophan or to whatever fluorophore that you are studying. But these equations are related to the technique, the methodology of measurement. Yeah, yeah, correct.
Are these parameters that affect, let's say, the intensity of fluorescence, are they also going to change the lifetime or
No, they might change, but the lifetime, so one of the features of the lifetime is that it doesn't depend on the, in other words, if you have a concentration of 1 nanomolar fluorescein, and then you prepare two other solutions of 10 nanomolars and 100 nanomolars. The intensity varies in each solution and is almost linear within a range. The lifetime is the same. And this is one of the also of the reasons that people want to use lifetime, because it provides, it's a measurement that is not dependent upon the concentration of the fluorophore. So this is a depiction of how time domain instruments called a time correlated single photon counting works. So typically we use pulse sources with a set repetition rate. So we send a pulse, boom, boom, boom. And the pulses are depicted here in the time. So we send a pulse, but there is no fluorescence detected, so nothing happens. We send a pulse here, and now, wow, there is a photon coming out. So the machine measures the time between the arrival of these photons to the detector and the next pulse. So this time is placed on the histogram at a certain point. Now, again, a series of two more pulses, no events. Another event, another pulse, and there is another photon. Now, this photon gets a little delayed, so we're going to finish up here. So we repeat this experiment thousands of times, and we build a histogram. And this is an example of all these little dots on anthracene. And now it's on a logarithmic scale also, but this would be a single exponential decay, and so it's on a logarithmic, it's just a straight line. And then we fit this decay curve, and we determine the lifetime. In frequency domain, the approach is totally different. We have our sample, we have a light source, and we amplitude modulate a frequency f, the light source. And then the fluorescence goes to a light detector, which translates the light into an electrical signal. And the fluorescence is still modulated at the same frequency. The gain of the detector is modulated at this other frequency, the same frequency plus an offset frequency. And at the output, we measure the phase shift of the fluorescence and the demodulation. So for each modulation frequency, let's say about 10 megahertz. 10 megahertz, well, we had measurements here at 9 some megahertz. We measure a phase shift of about 10 degrees, 10, 12 degrees. And we measure a demodulation of 0.09, whatever it is. So we repeat the measurements at several modulation frequency, and we get these two curves, one for the phase and one for the modulation. Both methods, in reality, are very similar. They are the same, because one is the Fourier transform, mathematically is the Fourier transform of the other. And there are advantages and disadvantages depending upon the application in using one over the other. But we won't go into that. And by the way, if any of you is interested in knowing more, next week we will have the practicals, but otherwise you can ask after the lecture. So this is what you will be using next week, and these are some examples of decay time measurements. Time domain, nata, 3 nanoseconds, 3.1 nanoseconds. The wavelength is slightly different, so maybe that's why there is this slight difference in the decay time. This gives you an idea of how short you can measure, about 80 picoseconds, 77, 78. Frequency domain, time domain, the same compounds. This is a rotational correlation time, so the technique can also be used for big molecules to study how they rotate in solution. And this is an example of a coumarin 6, where there is this rotational correlation time of 2.6 nanoseconds. And this again, the temperature is different, and so that's why there is this difference in the rotation. And you may read out in this way that when the temperature is higher, the motion increases, the molecule rotates in an easier way, and so it rotates faster. And that's why the rotational correlation time is shorter, 2 nanoseconds. And this is the way the data analysis is done, but this is done in the background, in the instrumentation. So in one case, we build a function, a theoretical function of the decay of the number of photons, and we minimize it. It's a chi-square function. In the other case, we use the phase shift and the demodulation. This is wrong. We should have a factor of 2 here and 2 here, like here. And these are some of the applications that, for instance, in FRET, that is used ubiquitously, when two molecules come close to each other, close means below 10 nanometers, so very close, the energy of one molecule can be transferred to the other molecules. The decay time decreases, and then we can study binding processes by just measuring the decay time of fluorescence. This is another type of application which is used in mainly medical applications. Again, it's based on FRET, and we go to study, to measure the decay time of a donor in presence of an acceptor. In this case, these are a system of antibody, antigen, and the decay time decreases when it's very close to it, and otherwise it doesn't change much more. This is another example of a sensor. Well, it's a bad drawings, but the idea here is that suppose we have an analyte, and we want to detect the presence of this analyte. For instance, this can be the oxygen in the fish tank, or it can be the CO2 into a fermentation chamber. If we are able to build a sensor whose lifetime is affected by the presence of the analyte, then we can do this type of measurements. Of course, in the fish tank, it's not that important because one can other methods like Clark electrode, stick it in the fish tank and measure the oxygen for the fish. But there are some applications where this is not always the case. This is an application from Dr. Thompson. He's a researcher out in Baltimore. His problem was to detect copper ion, the concentration of copper ion at different levels in the seawater, at different distances from the coast. So he used one of our instruments, put it on a vessel, and actually this is the vessel, the RV Nord, that is stationed at Woods Hole Institute. He put the instrument there, and he connected fiber optic cables to the instrument that was 250 meters long. On the tip of the fiber optic, he actually placed the proper chemistry. So this is the trick here. You need to put the proper chemistry that interacts with the presence of copper ions. And well, they measure the concentration of this copper ion at different distances in the Atlantic from the coast and a different depth. And they build a map. How? Because he first built a calibration curve where he detected the phase angle and the modulation. This was a frequency domain instrument. And this calibration curve had values for the phase angle and the modulation for different concentration of the copper ion. So whenever he was measuring a value, he could detect, he could infer the value of the concentration. So this is just an example of how lifetime information can be used to solve a real problem. Now let's talk about the last parameter of the 5 parameters that characterize the problem. And this is the polarization. Light is an electromagnetic wave, and so there is a direction of propagation, and there is an electrical field, and there is a magnetic field, and they vibrate at perpendicular to each other and perpendicular to the direction of propagation. The wavelength of light is given by the time it takes for an electrical field to do a complete swing or a magnetic field. For the polarization, we are getting concerned only about the electrical field, so we don't care about the magnetic field. What is unpolarized light? Well, unpolarized light, which is light from the sources like these lamps or the sun, is a superposition of different kinds of polarization. Now, if we start with unpolarized light, we can always make it polarized by using what is called a polarizer. A polarizer is a device that gets unpolarized light, and on the output, it gives you plain polarized light, although there are devices that give you circular polarized light as well. Typically, there are Polaroids or calcite polarizer. Calcite is just a mineral that is mined and cut. It's a birefringent mineral that is cut for this type of applications. Now, molecules have, when they absorb light, they have what they're called transition moments. And there are preferred transition moments. These are, in this case of molecules, for a transition moment in this direction for the first ground state and first excited states, or ground states to the second excited states. Light is absorbed only if the light that excites the molecule is more or less parallel to the transition moment of the molecule. If it's not parallel, there is no absorption. So it's like if the molecule would be invisible to light. If they are exactly parallel, there is maximum absorption. If the molecule is rotated to a certain angle, molecule, the transition moment, the probability goes like the square of the cosine of the angle. To build an experiment for polarization is fairly easy. So let's say that here we have our solution. We have a light source. We come in with a polarizer, and this is our vertically polarized light. And then the fluorescence can emit in different directions, but here we have an analyzer that we can rotate, and we can select the plane of polarization, and then the detector that looks at the light. Conceptually, it's fairly easy. We can build these quantities. One is called polarization, the other one is anisotropy. And the polarization is simply the difference of the detected light in the vertical plane minus the horizontal plane divided by the sum. The anisotropy is the same. The only difference is that there is a 2 here. Now, it is interesting to see that some papers use the term polarization, some other papers the term anisotropy. It all depends a little bit about the disciplines. Typically in the life sciences, for historical reasons, people prefer to use polarization. But in physics and chemistry, people prefer to use anisotropy. The reason is that if you do anisotropy, the formula are much simpler because this is actually the total light emitted by the sample, and so this simplifies some of the calculations. Anyway, practically they are the same, and you can relate, you can do some calculations and find out that the anisotropy is related to the polarization by this formula. While the polarization varies between -1 and 1, the anisotropy is -0.5 and 1. Now, how does this relate to the real samples? So in real samples, we need to deal with the fact that the molecules that we are trying to analyze in a solution are not necessarily all vertically or parallel to our excitation light. And above all, they don't stay that way just because there are other phenomena. For instance, the first one is Brownian motion. There is temperature, so the molecules in the water, they move around and they kick the fluorophore. If it's fluorescent, the fluorescent rotates and so on. So if we do all the calculation, we find that anisotropy is equal to this particular number, where this angle is the average angle made by the emission transition moment of the molecule. And I don't go into the calculation, but the average of this angle is 3.5, 3/5. And when we plug it into the anisotropy formula, we get a maximum of 0.4. So 0.4 is the maximum anisotropy that we get if I excite parallel and the transition moment of the molecule is parallel. Well, that is the best scenario. So that means that we cannot go above 0.4, is our ceiling. And, but we can go below. And in reality, we never get 0.4 because of a lot of practical issues that deal with the experiments. Now, what happens if the transition moment is not parallel, but if it makes an angle? So the formula becomes a little more complicated. So there is this term that we just saw. And then there is the angle between the absorption and emission moments. And here we have two scenarios. One, if this is parallel, so we go back to the 0.4 that we found before. If you plug in 0 here, this is 3 minus 1, 2 divided by 2, 1, and we are only left with this part of the formula. If this, on the other hand, is 90, we find R0 minus 0.2. So this tells us that the anisotropy varies between these two values, minus 0.2 plus 0.4. So if somebody comes to you and says, oh, I measure minus 0.3, well, something wrong. Forget about it. This is an example of erythrosine. Here we have the excitation spectrum. So again, this is the range of wavelengths that the fluorophore can absorb radiations at. And here we measure the anisotropy. You see that back in the UV, the anisotropy is below 0. Well, this is polarization, but it's the same. It's below 0. And then it becomes 0 at around 350, and then it increases, and then it almost stays constant all the way up here. But this is just to give you an idea of how the polarization goes for these molecules. And it's important because it also tells you that not only when I give the value of the polarization, I need to specify the wavelengths where I need the polarization. Well, so this is a picture of how the polarization goes, but in reality, the polarization can change because of the environment. And the first example that, the first culprit is really the Brownian motion. The Brownian motion arises because of temperature, and it depends on the viscosity. You have it here. And we can follow a relationship for isotropic molecules that follows this law. And by the way, this is a digression. We can calculate the steady-state polarization by calculating the average anisotropy by doing over the time, over the entire time scale. And we found an equation that actually was found by Perrin the first time that is kind of elegant because it relates the actual anisotropy with R0, the limiting anisotropy, the 0.4, with the lifetime. And this is interesting because by measuring the anisotropy, we can actually evaluate the lifetime. So by measuring a parameter that is just a steady state parameter, we can actually know something about the decay time of the molecule in the nanosecond scale, so in the 1 billionth of a second. And this is just an example for a protein. And ANS, when it's linked to BSA. We plug it in, and we find that by measuring the steady state, the R0 and R, we find the decay time is of the order of 20 nanoseconds. It's actually 22, so it's pretty good, pretty close. So but back to the main problem. For complicated molecules, this equation becomes a little more complicated. So these are anisotropic rotators and hinderer rotators. And this just tell you that the theory becomes a little more complicated. It has to deal with a specific problem that you have to deal with. But what is more important, you just try to understand why this is important. This is important because it has some practical application, and one can, in spectroscopy, separate excited states, but one can use the polarization to measure the viscosity, orientation, dynamics. This is some of the application antigen, antibody, and these some of the applications in molecular biology. And in fact, for instance, this one, immunology, I have to stress, this is very important. There are machines out in the hospitals sold by Abbott Labs, and they are based on polarization. So when a lot of tests that are even the HIV virus, they have an assay that is based on polarization, and it uses specifically this phenomenon. So I will stop here. And again, so there are 5 parameters in fluorescence: excitation, emission spectra, quantum yield, lifetime, polarization. I just wanted to give you an overview of how some of these parameters can be used for some specific applications. That's it. Thank you.
Thank you, Ben. Do you have any questions, guys? If not,
Yes,
oh, let's see Dr. Barbieri tomorrow morning again.
sorry. Yeah, go ahead. To time domain. So if you follow a problem that is a monitoring problem, like the one that I show with the fiber to go to measure the copper ion in the ocean, you just simply do, you drop your fiber and you just want to measure right away. in that type of application, the frequency domain is superior, because otherwise in the time domain, you need to waste some time to build the histogram, do the analysis, while in the frequency domain, you don't need to do that, because you already have your calibration done. Another type of advantages is when you're measuring the rotational correlation time. Or let's say you have a decay, a fluorophore with 2 decay times. A short one, 100 picoseconds, and a long one that is 10 nanoseconds. Now you vary the environment, and the change in the environment affects the short decay time. From 100 picoseconds, it might go to 80 picoseconds. Well, this is in time domain, is very difficult to see. But in frequency domain, is easier. So again, it depends. On the other hand, time domain is more sensitive than the frequency domain.
So, any information I showed you mentioned that you can study the molecule. So, this relaxation in the S1 level happens pretty fast. So, just want to know how does it compare to the second?
Oh, yeah, it's of the order of 10 to the minus 15. The internal relaxation of the molecules to the grounds, to the first excited level from the upper levels is very short. So the fluorescence is typically of the order of 10 to the minus 9 seconds, so 1 nanoseconds, but it can be 100 picoseconds. But that is much shorter.
Second question is you mentioned the area equation.
Yeah.
That measuring.
Yeah.
You can measure lifetime. So in terms of experimental implementation of each one, we can compare.
Well, no. Yeah. I just wanted to show because it's kind of nice, and because, so Perrin discovered it in 1926, 27. So at that time, the instrumentation was primitive. And that gave a way to evaluate the decay time by using steady state measurements. But of course, people didn't have a way to check, is it correct or is it wrong? But it is correct. I mean, the formula comes out to be correct. But you don't use it, you just use it as if you have a system, let's say you have typically a protein, you know what is the molecular weight, you plug it into the formula, so you know, oh, well, the decay time might be 5 nanoseconds. So you use it as a guess. It's a fairly good guess. Yeah. Yes. Yeah. You want to measure it. Yes.
Okay, well, if you don't have any questions, you can have 5 minutes to stretch your legs and come back for the next round. Thank you, Ben.
Oh, you're welcome.